class. Can you see the presentation? Please unmute and tell me. Can you see the presentation? Hello, somebody?
Yes, ma'am.
Okay.
Yes,
Okay.
ma'am.
Okay. So this is module 4, and whatever I did in the previous classes was out of syllabus portion to aid this, okay, this particular topic. Somebody asked me whether we should study it for the exam or not. ಹಳೆ ಕ್ವಶನ್ ಪೇಪರ್ ನೋಡಿದ್ರೆ ಒಂದು ಸ್ವಲ್ಪ ಬಂದಿದೆ, but not for a lot of marks. So what I'll say is you concentrate on this a lot, this portion, ಯಾಕಂದ್ರೆ ಇದರಿಂದ ಅಂತೂ ಮಾರ್ಕ್ಸ್ ಬಂದೇ ಬರುತ್ತೆ. And this you read it once and go. ಸುಮ್ಮನೆ ಅಂದ್ರೆ ಚಾಯ್ಸೇ ಇಲ್ಲ ನನಗೆ, ಸೆಕೆಂಡ್ ಕ್ವೆಶನ್ ತುಂಬಾ ಕಷ್ಟ ಆಯ್ತು ಅಂದ್ರೆ ಫಸ್ಟ್ ಕ್ವೆಶನ್ ಅಟೆಂಡ್ ಮಾಡಕ್ ಏನಾದ್ರೂ ಇರ್ಲಿ ಅಂತ. So I'm not going to do this today. I'm going to upload this. Aita. So conversion from PDF to CFG, CFG to PDF, and decidable, undecidable questions. I will upload them. Give me just 2 days. I'll upload it before. ಅದರಲ್ಲಿ 2 ಕ್ಲಾಸ್ ಅಪ್ಲೋಡ್ ಆಗಿದೆ, ನೀವು ಇನ್ನೂ ನೋಡಿಲ್ಲ. ಇನ್ನು 2 ಕ್ಲಾಸ್ ಇದೆ. I will upload it before Wednesday. So today I'll start with Turing machines. Okay. Amazon Prime ಅಲ್ಲಿ ಒಂದು ಮೂವಿ ಇದೆ. If you are interested, you can go and watch if you haven't watched it. It's about this fellow Alan Turing. His story, it's amazing. If he wasn't there, the computers wouldn't have been even invented. So ಅಂತರದಲ್ಲಿ ಇವತ್ತೇನಿದೆ ಅಲ್ಲ, all of us, whatever profession we are in or you are aspiring to be, everything is because of him. And I think you should see that movie, ಆಯ್ತಾ? Alan Turing ಇಂದು. It's there in Amazon Prime. ಹೀಗೆ ನೋಡಿ ಒಂದ್ಸಲ. So we'll start with the Turing machines. So what we need to know about this Turing machines is, today I'll do only theory. From tomorrow we'll start designing. Okay. Any algorithmic procedure, if I and you can carry out, then it can be carried out by Turing machine. Turing machine came earlier, so it can do anything that a human can do, algorithmic procedure. Okay. Or today's computers, whatever they do, can also be done by the Turing machine. So everybody has agreed to that. Whatever Alan Turing suggested, model or machine, okay, it's an ideal theoretical model of today's computer. Okay. So Turing, what he assumed is, whenever an algorithm or computation is done by a human, so the person writes symbols. Okay. So he says that whatever we can do, we can convert it into symbols on a one-dimensional tape, which is divided into cells. So something like this, any string or any processing, anything we do, okay, we can take a tape, we can divide them into cells, and we can write some symbols over here. Okay. And then we can scan one symbol at a time, like this one or this one. So earlier days we had tape, and there was something called as a read and write head. So this cell, if it's there under the read and write head, it means that I'm going to either read or write or do something with this particular symbol. Okay. Some operation, right? Read operation or write operation. Or if I don't want to do anything, I can move towards right of a symbol. So if I'm at B, if I go like this, right of a symbol movement, right? Tape can move here, or tape can also move towards the left. So that's what he says. So we can scan one cell at a time and perform these operations. Either write a new symbol in the cell, or you can move towards left of the present cell, or you can move to the right of the present cell. Okay. So he said that we can use only these 3, and then we can actually design a computer or computing machine. So you can see a model over here. This is our Turing machine model. Okay. This is the tape I am talking about, and this is your read and write head. Okay. Finite control is the subject you are studying, isn't it? So tape is divided into cell. You know that your disk is divided into sectors, tracks, etc. You have studied like that, no? So every tape can be divided into number of cells. So this is your basic diagram or basic model of the Turing machine. So if You can see here A1, A2, A3 are symbols. B is blank. We can also use blank, okay? And we can assume that this particular tape is of infinite number. And whenever we say we will design a Turing machine, that logic that we create for Turing machine, that will be stored over here in finite control, and it will control what I do next. That is whether I am going to move towards left, move towards right, or I'm going to read a symbol, write a symbol, whatever. So that's determined by the finite control. Okay, so things to remember now: every cell can contain only one symbol. Okay, and the input and the output of this finite automation are affected by the read and write head. Read and write head means the one which will be over a cell. Okay, so what can we do in a single move? In a single move, you can see what is there under the read and write head. So you can see here, no, what is there under the read and write head. So after examining what is there in under the read and write head, what can you do? See, you can add a new symbol, that is writing, correct? Or you can do the motion to left or right. You can also determine what is the next state and when to halt or not to halt. So I will repeat again. So if you have a tape and if this is my read and write head, I can write a symbol over there, or I can move the head towards right or towards left of this tape or cell. Okay, and then I can also determine, for example, maybe in that finite control I am currently at a state called as Q0, just like your finite automation, any other finite automation. So after moving, you can also change the state to Q1, etc. So you can also determine what will be the next state of the automation, and there is a possibility that I have to halt, isn't it? I have to know when to stop. So should I stop or should I continue with the operations? So that also can be determined. Now coming to the formal definition of the Turing machine, you can define it using 7 tuples. Okay, so 1, 2, 3, 4, 5, 6, and 7. Out of these, you should be familiar with a lot of them already. For example, Q, this is a textbook change. Okay, so if we use K in the previous textbook, from Turing machine onwards, you have the second textbook, which is Theory of Computer Science, Automata, Languages and Computation by KLP Mishra and N. Chandrasekharan. So some terms will be slightly different, but it's easy, no, because we have been naming all the states as Q1, Q2, etc. So Q is the finite non-empty set of states. This we already know. These are the alphabets, correct? One thing you remember, so those are the inputs symbols, and along with the regular non-terminal symbols we talk about, we will also use a special symbol which is a blank symbol. So some people write it as B or some people write it as B dash. This is a blank symbol, and blank will appear on the tape, but it is not considered as a input symbol. I'll repeat again. So you will have this sigma. Sigma is a non-empty set of input symbols. And we also say it's a subset of tau. Okay. Tau you can see is a set of tape symbols. We had used it for stack in PDA, tau, right? So here, tau is a finite non-empty set of tape symbols. So what all can be there in the tape? Obviously, all inputs can be there in the tape. Along with the inputs, I can also have a blank symbol on the tape. That's what we mean by this. So it's a non-empty set of input symbols. It's a subset of tau, which is a tape symbol. But you see here, B will not be a part of sigma. Okay, so B will be a part of tau. It will be there in the tape, but it will not be there in the input. Okay, and because we introduced a special symbol to represent blank, so B is nothing but it's a blank. Okay, Q0 you will know that it's a starting initial state. right? It belongs to Q. It's an initial state. F, so far, A we used to write, no, set of acceptance states. So finish. So F is a set of final states here, and delta is the transitions we are going to design. So when we design, we are going to design transitions. So if you are currently at some state, you have seen some input symbols. On seeing the current symbol, whether you will change the state, you will read, you will write, you will uh, move towards the left, right, whatever action that is there, that is determined in this delta. So and in the exam, you have to properly write, okay? I mean, definitions, formal definitions are very important. In test also, all of you have written what you have understood, it is correct also, but they are not formal definitions. Formal definitions are important from your textbook. Please do write the formal definitions. Antadén tumba illa definitions alva. CFG, regular grammar, PDA, Turing machine, very few formal definitions. DFSM and non-DFSM. ಆಮೇಲೆ ಒಂದರಿಂದ ಇನ್ನೊಂದು ಮೀಲಿ ಮೆಷಿನ್, ಮೂರ್ ಮೆಷಿನ್, ಒಂದರಿಂದ ಇನ್ನೊಂದಕ್ಕೆ there will be very few changes. Most of them will be same only. Okay, so please write the formal definitions. I'll repeat again. A Turing machine is a 7 tuple. So these are the 7 tuples. Q is set of states, sigma is input symbols, and it's a subset of tau. Tau is the tape symbol, and blank is not a part of sigma. Delta is the transition function. For example, you can see one transition function here. You are at state Q and input symbol is X. Maybe you will be moving to Q dash, some other state. This input symbol may be replaced by another symbol, and this is the direction. After this, whether you are going to move towards right or move towards left. So you can write it as R or L. Okay, so that is your delta. Q naught is your initial state, B is the blank, and F is a subset of Q, which represents a set of final states. Okay, so whenever we say design a Turing machine, how do we represent the Turing machine? There are 3 ways of representing the Turing machines. The first one is by using transition diagram. One more is using the instantaneous description. And the third one is transition table. I think we have done this for all the things till now. For DFSM, you can write the transition diagram or transition table or even instantaneous description. For everything we have seen, isn't it? Whether it's a DFSM or it's a PDA, for all of them we have used all these 3 representations, possibilities. So same with the Turing machines. You can represent it using any one of these 3. Okay. So we'll see how to represent and what is the meaning for each one of them. Let us take the first one, representation by an instantaneous description. Okay. So it's easy. Let us say the Turing machine, the initial ID of the Turing machine M is alpha, beta, gamma. So beta is the present state. Okay, and the input can be split into alpha and gamma, means whatever is before. So you can see here, this is a blank symbol, A4, A1, A2, A1, A2, A2, A1, symbols are there like this, isn't it? And this is the state. Beta is this state. Okay, currently beta is this state, and then I am going to divide the string, whatever is there here, from A4 to A2. Okay, into alpha and beta. Alpha and beta. Sorry, alpha and gamma. Sorry, beta is the state. So I'm going to divide it into alpha and gamma. So what is the first symbol of gamma? You see here, this portion is gamma. Okay, this portion is gamma. So the first symbol of gamma is the symbol which is there under the read and write head. Okay, and it has subsequent symbols of the input strings which we have to check. And what is alpha? Alpha is whichever is there towards the left of this particular thing. So all these which are there towards the left are called as alpha. Again, I'll repeat. whenever we design a Turing machine, it can be represented using three denotations. One is using the instantaneous description, then using the table, transition table, and also using the transition diagram. So we are taking the first one, and this is representation using the ID or instantaneous description. Very simple. So we say that we can represent it using the snapshot of a Turing machine. Snapshot is what you see here. Okay, at each stage, whatever we can show you at each step can be considered as one snapshot of that step. So how do I show an ID for Turing machine? I show an ID for Turing machine by dividing whatever is there on the tape into alpha, beta, gamma. What is beta? Beta is the present state of the machine. For example, here Q3 is shown. This is beta. And what is gamma? So if currently we are pointing to this A1 or reader right head is there towards A1, this A1, then this is going to be my gamma. And the first symbol is the symbol which is there above the read and write head. And whatever is towards the left of it, that is your alpha. I hope this is clear. So you have divided it into two substrings, alpha, gamma, beta is state. Okay. So the same thing is shown here, right? So you can see this Q3, this is present state. And what is there under Q3, I mean under read and write head, that is A1. And the write sequence is A4 and A2, right? This is gamma, correct? And this is beta, and whatever is towards the left, this is alpha. These B's are not symbols. Don't get confused of A and B alphabet, okay? In this case, Turing machine, always remember B represents blank, okay? If at all in the problem I need A and B, no, then we'll represent blank using a dash over B to differentiate this symbol B and this B. Otherwise, if B is not a part of string, then we are using this alphabet to represent blank. I hope this is clear to you. Okay. So let me just take one small example and write an ID. Okay. After this, I will move on to how to represent this Turing machine using the transition table. So let us suppose have a delta transition, and delta transition can be some state. Okay. Let us say Q, and xi is equal to PYL, something like this. So let us assume that we are going to process some input string, and this input string could be let us say x1, x2 and up to some length xn. So currently for this snapshot, xi is what is there under read and write head. Okay, and q is the current state. So this is our beta. Okay, before processing, and after processing, this is what it's going to be. All right. So let me write this whatever I told you as x1, x2 up to xi minus 1. This is our alpha, correct? Xi minus 1, and currently the read and write head is under in a state q. So this is beta. Whatever comes to the right side of beta, so this is xi minus 1, so will be xi, and this is where our gamma begins. So it will be xi plus 1 up to xn. Okay, xn. I hope this is clear. So this is current state. So after processing xi, this is what has to happen. So how will I show it? Okay. So how will I show it? After processing xi, okay. So the resulting ID is, obviously you will have from x1 to x2 etc. up to xi minus 2. I want you to figure out why I stopped over there. I'll explain, but can you just figure out why I have stopped over there by yourself? I wrote something like this. We were at state Q. We were processing this symbol xi, and after processing, this is what has to happen: p, y, and l. L, I told you this is a direction, so L is for left and R is for right. Correct? R is for right. So can you tell me what is it that is happening over here? Did you figure it out? Okay, if not, since we said we have to move towards left, right? From the current position, I have to move towards left. So move towards left means after x minus I2, now my read and write head has to be over here. So I moved towards left. This is clear, I hope. And then I said state of change from Q to P. So this is state of change from Q to P. Okay. I hope this is clear. And then the rest of it. In the rest of it, now what is, yeah. So that's what we have to do. That's all, right? So this is how we write. So let us say if I is equal to N, I is equal to N. This we have taken for Xi, no? Some Xi. So if at all I is equal to N, that is the last symbol, Xn, correct? So if at all it is for I is equal to N, then the ID will be something like this: X1, X2 up to Xn minus 1, Yp and B. Why? You can see here, if you are processing N, you have to move left, right? So that is Xn minus 1 and replace the state by Y, right? And then what? After Xn, nothing is there. So it's going to be a blank. It's going to be a blank. So these are the moves that are possible for a Turing machine. All right. So I hope this is clear. So this is what we'll use in the, we'll also use this while we are solving some problems later. So as an instantaneous description, how I can show is, you write this first and then write this symbol. We have used this for all IDs, right? And after this, you can write this. So current state leads to the next snapshot. So this is the representation by transition table. Now the second type of representation. Same thing, whatever we studied, how can we represent it? Using transition table. So basically we will be representing delta, right, in the form called as a transition table. So let us say there is a transition like this, delta q comma a, right, will result in gamma, alpha and beta, right? So how do we represent it? So we write alpha, beta, gamma under alpha column. I hope these terms are familiar. What is alpha? Alpha is the string before the before taking any action. That's part, left part, right? Gamma is the right part, also including the symbol which is there under the read and write head. And beta is your current state, correct? So we are going to write alpha, beta, gamma under the alpha column in qth row. So what is Q? Q is the current state, correct? Q is the current state. So uh, let us see one example, okay, for the same thing that we saw. So let us say we have states. Forget about what we have designed this for. Okay, I'll tell you what is this problem and the Turing machine is for which problem, what is the solution. So right now we are not bothered about it. We are just seeing how we can represent. So when you represent it using the state, we'll have a present state. Let us assume the states are Q1, where initial state is Q1. And let us say you have Q2, Q3, Q4, and Q5. And final state can be represented with a circle. Okay. So after this, we will also write one more column called as tape symbols. Let us say for some problem we have three tape symbols. One is B, which is blank, and maybe 0 and maybe 1. Okay, these are the three symbols. Again, listen to it. Don't worry about this is going to solve which question. Just understand the entries in the table. When we design, we'll design all those entries. Okay. So currently you know that for some solution, we'll need 5 states: Q1, Q2, Q3, Q4, and Q5. Initial state is Q1, final state is Q5. So this is present states. What else will be there in my transition table? I will have tape symbols. So tape symbols are blank, 0 or 1. Okay, these are the possibilities. All right. So the entries can be something like this: 1LQ2. Okay, 0. Again, don't worry about this. You will understand how to design this. Right. So just know that there are some entries over here. With the instantaneous descriptions information, can you make out what is L and R, and which is alpha and which is beta, etc.? 1, 2, 3, 4. Don't worry about these entries. We will design this. At that time, we'll see how to design this. Let us say your table is like this. Okay. So, how do we show the computation sequence? This is designed, okay? When I ask you to design a table, you will be designing something like this. These are the notations we are trying to understand here. Okay. So let us see how to understand what are the moves that we are going to make. So we will show the sequence of all these computations using the tape symbols and the current state. That's why those are the part of the table. Okay. So let us say Turing machine, if at all I have something like this, okay, A1, A2, some symbols, let us say AJ plus 1, again some symbols up to AN. So the Turing machine is in state AJ. Okay, Q is over here. It has to read J plus 1. In that case, how do we write this? We write it as A1, A2, AJ, Q, and AJ plus 1 and AN. Okay. I'll again repeat. If I have to read the state AJ, excuse me. If this is some string, like zeros and ones are there, some string with symbols A1 to AM, and the next symbol I need to read is A, J plus 1. And if I am in the current state Q, this is how I am going to write. This is alpha, current state is beta, AJ plus 1 is the next symbol to read. So this is obviously going to be a gamma. Okay. So now let us just take one example and use it to use this table, just to see how to use this table. Let us say you are in state Q1. All right. and the input string is 00B. That means 00 followed by a B. Okay. So you can see here this is Q1. Which one you have to see? This one, right? 0. The next input symbol that you need is 0. So this will lead to 0 Q1 0 B. So why is it? So you can see here under 0 I had this. So it asks me to keep 0 as 0. So 0 I have kept unchanged. Okay. It also tells me move to right. Right. So and the state still remains Q1 itself. So what I do is I move this Q1 towards the right by making no changes to 0. Alright. Now if you see this Q1 again, the next transition will be again Q1 on 0. So again Q1 on 0. So what it will be? 0 0 Q1B. Why? Because Q1 on 0 tells me keep 0 as 0 itself. Just move towards right. And the new state is Q1. So all that I did was move towards right, kept 0 as 0 and kept this change. I didn't change the state also. All right. So this is my next symbol. Now what do I do? I have to check for Q1B. Correct? Next. So you can see Q1 and B here. If you see Q1 and B, what does it tell me? You change the blank to, because Q1 on B, right? So change the blank to 1. Move towards left and make the change of state to Q2. So how will I represent? So 0 will be as it is. This B will be changed to 1 because it has been told to do so. And I have to move towards the left by 1 position. So I have to come here. Okay. And the state will change from Q1 to Q2. So this is my next description. I have to check for Q2 on 0 now. You see here Q2 on 0. What does it say? It says change this to blank, correct? Q2 on 0 tells me, not blank, Q2 on 0, this one, 0L Q2. So keep 0 as 0. Which is 0? This is what we are talking about. So keep 0 as 0, move towards left and keep the change state to Q2 itself. So my next one will be Q2001. I hope you understood. See, unchanged, right? 0. So unchanged. Don't change 0 to anything else. State also hasn't changed. It is Q2, no? So state is still same. Just move left. So from here, Q2 has moved left. Q2 has moved left. Now Q2 on 0, right? So what is Q2 on 0? Again, same thing, no? You have to move towards left. See, as you go fast, you will not even bother much. Q2 on 0, you will understand that Q2 on 0, it is remaining 0, it is remaining Q2. Only thing is I have to move left. So I move left, but there is no symbol to move left. So I will introduce a blank. So 001. Okay. Next, Q2 on blank. Q2 on blank is this. Again, see, blank is unchanged. You move towards right side and go to state Q3, right? So blank is unchanged. You move towards right and make the state as Q3, okay? And remaining things remain same. Now what do I have to see? Q3 on 0. So Q3 on 0 here you see. Replace 0 by a blank. So after Q3 this 0 is there, no? You have to replace it by a blank. Move towards right. So Q3 has to move towards right. And it has to become Q4. So blank, blank, Q4 and 01. Blank, blank, Q4 and 01. So next what will you see? Q4 on 0. So if you see Q4 on 0, you can Q4 on 0, 0 remains 0. Q4 also remains Q4. That means you are just going to move towards right. So blank blank remains as it is. 0 remains as it is. You moved right. Okay. Next Q4 on 1. You can again see 1 remains as it is. Q4 also remains as it is. So again move right. So it will be BB01 Q4. Correct? And after this, obviously, there is a blank. If nothing is there, no, before or after, we have to introduce a blank. So now Q4 on B. You can see here Q4 on B. Right? So blank has to be changed into 0. Right? So this blank has to be changed into 0. Move right and make it as Q5. So BB01. This will become a 0 and this will become a Q5. Okay? Like this, we are going to continue. Is this clear? Until there is a place to stop. All right. So, for example, if I reach Q5 on 0 or Q5 on 1 or Q3 on blank, I'm going to stop because there are no transitions. I hope what we have done is clear for you. So, I'll stop for today. This is how we represent using the table. Tomorrow we'll see how to represent the same thing using diagram, and then we'll start designing the Turing machines. Okay, so you can start uh, marking your attendances and leave the class.